What if we don't share things equally? Well, then we're going to make polar bonds and polar molecules. Let's take a look at these in this section. Be able to define nonpolar covalent bond. This is where electrons are shared equally between the atoms. Polar covalent bond. Well, obviously, this is where electrons are shared unequally between atoms in a covalent bond. Polar molecule. A polar molecule is a molecule with polar bonds, making one end slightly negative and one end slightly positive. What's a dipole? Well, it's a definition of one of those ends. So one of those two poles in a polar molecule with a slightly positive charge with a slightly negative charge. What are van der Waals forces? Those are the weakest attraction between molecules. We'll see how they work a little bit later. Dipole interactions are when you have two polar molecules attracted to one another. Think like a little magnet, mini magnets getting close to one another. Dispersion forces are just the motion of electrons, which occurs even between non-polar molecules, making some slight polarity, kind of a slight dipole moment, and making things attracted to one another. Hydrogen bonds are attractive forces when you have a hydrogen covalently bonded to a very electronegative atom, like water or fluorine, which causes the hydrogens to get a slightly positive dipole and form slight attractions towards the negative side of another molecule. And network solids I'm saving till the end. Differentiate between polar and non-polar bonds. Predict whether a bond will be polar or not using electronegativity. So this goes to HSPS1-1 right there. And differentiate between types of attractions between different molecules. Covalent bonds are about sharing electrons, but not all covalent bonds share electrons equally. So we're going to, in class, spend quite a while reviewing electronegativity, and you need to. So if electrons are shared evenly, you get nonpolar covalent bonds. That's bonding electrons are shared evenly. So your diatomic molecules are going to have nonpolar covalent bonds. Carbon and hydrogen bonds are nonpolar. You see a lot of carbon-hydrogen bonds that are going to be nonpolar. Polar covalent bonds are when you have uneven sharing of electrons. So for an oxygen-hydrogen bond, the oxygen gets the electrons more often than the hydrogen does. Carbon and oxygen do not share equally, so the oxygen will get more of the electrons than the carbon. And these make polar molecules. So polar molecules have this one end that's slightly more positive and the other end slightly more negative, so they're kind of like a mini magnet. So the molecule with two poles is called a dipole. If it had more than two poles, it'd be like a tripole or something, but let's not look at that. Let's focus on this guy right here. Hydrogen chloride has a slightly positive side and a slightly negative side because chlorine is more electronegative than hydrogen, so it takes the electrons more often, causing a negative charge on the chloride side and a positive charge on the hydrogen side. Now, what do these do? What happens when you have polar molecules? Well, in a magnetic field, they'll actually all line up, so they're pointing the same way. If you have a negative charge and a positive charge, then you're going to actually attract, the negative charge will attract the positive sides of the molecules. And you're like, wait, so they all go different ways? No, they just line up. So they're oriented properly. And you can see that actually it's kind of cool. It's figure 8.24 gives a little bit of an example. They all just line up in a row. It also means that some of these are going to be magnetic. So water is actually magnetic, so it responds to the presence of a magnet. Well, what about something like carbon dioxide? It is polar bonds, and you see that it has slightly more negative sides. On the oxygen, you have two dipole moments. Well, the dipole moments are in opposite direction. Remember the shape of molecules? And that means it can't really line up. You can't line up with your center towards something. It doesn't work that way. And that makes it overall nonpolar. And polar solvents, like hydrogen chloride, or more importantly, like water, actually dissolve ionic compounds very well because the positive side of the dipole can be attracted to negative ions, and the negative side of the dipole can be attracted to cations. So this actually is really important later on and in the properties of water. Let's look at the different forces, different attractions between molecules. The weakest ones are called van der Waals forces. And those are two different types of van der Waals forces. The first is dipole interactions. Dipole interactions are attractions between polar molecules. Now, we've already looked at that. Over here, you're going to have your hydrogen, your chloride. Your hydrogen is slightly more positive. Your chloride's more negative, so you have attraction. That's your dipole interactions. We've already taken a look. They're weaker than ionic bonds, but stronger than, say, dispersion forces, which are the weakest of all molecular interactions. They are how electrons move even within an atom. So let's look at a simple atom, for example. You can see that the electrons can actually shift a little bit so that when you have two atoms next to each other, the electrons can go on one side more, which comes closer to this positive nucleus, and that pushes these away, making like a super mini dipole of a single atom. And that can happen with non-polar solvents as well, but these are very, very weak. Dispersion forces are the weakest forces. Dipole interactions are slightly more strong, and then you have hydrogen bonds. This is dipole interaction specifically with hydrogen, because in hydrogen, it's a very small atom with a single s orbital, and with that single s orbital, the valence electrons of hydrogen are not shielded from the nucleus by other electrons. So when you have a sigma bond with these hydrogens and, say, oxygen, those electrons are actually going to spend more time closer to the oxygen, meaning that your proton in the middle there, that little nucleus in the middle of a hydrogen atom, is actually going to be pretty positive, and that allows attraction to the unpaired electrons here on this side of the oxygen. So water has these hydrogen bonds, and most of the properties of water have to do with hydrogen bonds. When ice forms and ice is less dense than liquid water, it's because of how you arrange the atoms in respect to their hydrogen bonds. An ice crystal is because of the hydrogen bonds forming in these dipole interactions causing a certain shape. So it seems like a non sequitur here, but can you melt a diamond? Well, is it an ionic bond? Well, no. Ionic bonds do make a crystal, but diamonds are not ionic compounds. It is hard to melt an ionic compound, but diamonds are not ionic compounds. Well, let's think about hydrogen bonds. So you have crystals like ice. Diamonds look like ice, but diamonds don't have hydrogen bonds because it's just carbon-carbon, and carbon-carbon is a non-polar bond. So obviously that's not what's going on in a diamond. You don't have polar interactions going on like you would in water. Some solids, like a diamond, are made entirely of covalently bonded molecules, and this is a network solid. A network solid is where all of the atoms are covalently bonded to each other. So can you melt a diamond? No. It vaporizes to a gas at 3,500 degrees Celsius.